Okay, hello, my name is Willow.
My name is Feng.
And we are working with Dr. Harmon in the Physics and Astronomy Department alongside Dr. Richard Rottenbacher, who is an OU alum from the University of Michigan. And our NASA-funded research project is called Determining How Stellar Magnetic Activities Depend on Stellar Parameters Using Data from the Kepler Space Telescope.
Okay, first of all, we have to know where our observational data set come from. Well, our observational data set come from NASA's Kepler Space Telescope, which operated from 2009 to 2013. Its primary mission is to hunt for exoplanets, but it also carries out continuously long-term brightness monitoring for thousands of target stars. So we use this high-precision photometry for our star bodies. Here is a picture of the exoplanet transit light curve. As you can see, the exoplanet moves around the star. And when the exoplanet enters the region in front of the star, which is over here, it will block some part of the star, causing the brightness to decrease, which leads to be heading deep in the light curve. Here is a picture of the sun, and the spots on the sun is called sunspots. We study star spots on the stars, which are the darker, cooler regions on the stellar surface, which normally associate with strong magnetic fields. Here is a picture of a star spot light curve. As the star rotation carries the star spots and out of view, the star's brightness varies as a result. And you can see, when the spot is most visible, the brightness is also the thinnest.
Okay, so how are star spots formed? So the sun generates energy in the fusing hydrogen into helium in its core, and then it first transports the energy towards the surface. It first to the radiant zone via radiant diffusion, and then via convection in the convection zone. And convection is the rising and sinking of gas particles. However, due to strong magnetic field lines, it inhibits the horizontal motion of plasma, which is ionized gas, from moving side to side, but it can move easily up and down. So as a result, this prevents convection from occurring in these regions, reducing the flow of energy into them and why they are darker and cooler than their surroundings. So Dr. Harmon created a program called LI, which stands for light curve emergence. And this program takes brightness variations due to spots and creates a map of stellar surfaces shown on the right. So in these plots, the black markers represent the actual data and the red markers represent the light curves of the modeled surfaces. As you can see, the lower surface does a better job of fitting the data. However, it's covered in numerous small spots that are actually just noise artifacts that are like to explain the slight variation of noise in the data. So instead of trying to get the closest fit to the data as possible, we need to strike a balance between finding like a good light curve while not overfitting and producing a lot of noise artifacts. So here's an example of one of the hundreds of thousands of light curves that we have to analyze. We fit the light curves to various precisions of various levels of precision, and then we select the one that gives the best fit to the data while not being covered in noise artifacts like that one. So if we were studying one or a few stars, these selections could easily be made by hand. However, there's thousands of stars in the Kepler's data set, so this would be impossible to select all these. And no one has time to do that. So to solve this dilemma, we can create and use a CNN, which stands for Convolutional Neural Network. A neural network is a machine learning model that stacks artificial neurons in layers. Each neuron has an output value that is the weighted sum of the values that are connected to all the neurons connected to it in the previous layer. And then CNNs are often used to classify images like animals, human ones, and spots. So in this case, I created a CNN using TensorFlow and Python to identify star spots, how many star spots are in each image. And TensorFlow was created by people to make creating CNNs more efficient. I call my program Spot Classifier, and here are a few images that I labeled and then put into my program. And this program builds off of last year's SSRP work from Isa Rodriguez-Ortiz, who developed and created a CNN to classify stellar surfaces as being bad or if they were good. So this is how my program works. So first, I labeled thousands of stars based on if they had one spot, two spots, or if they were trash. And then I fed those labeled images into my program, and it split the data into 3 categories: train, validation, and test. And then the program started to train the data sets and then check its accuracy, and it ran 50 times. Each run of training is called epochs. And so the train set acted as flashcards where the answers of the images were labeled on the front, and then on the other hand, the validation set acted as flashcards with the answers of the labeled images were on the back. So check the validation images and then check its accuracy. And then lastly, it would test itself, so it would, where there was no labels given to it, so it had to make predictions and answer it based on what it learned from the training. So it would pick its guess. And then this was my accuracy and my results. So I ended with 99.54% validation accuracy and the test accuracy being 96.14%. And the graph represents the accuracy over epochs. So now that my program can sort images based on how many spots they have, I will feed my program images from the star's rotation, and it will select the surface that gives the best fit while not being covered in noise artifacts, and then also classify how many spots they have. So, for example, it would look at the top image, which has the best fit, and then it would classify it as trash, and then look at the second one, and it would choose the second one because it has the second best fit to the data. And then I will feed my images, my good images, from the program called Spot Identifier.
Okay, finally I will introduce the program I developed this summer called Spot Identifier. It adopts to pseudo-Mercator projection, which mathematically unwraps a spherical stellar surface into a flat rectangular map. This projection also maintains equal spacing in latitude. And also, as we move toward the North Pole and the South Pole, the number of matched patches gradually decrease, and this leads to area distortion. One example of area distortion is shown in the second picture. 2 identical artificial star spots look visually different. The one with higher latitude seems to be stretched onto the main plane map. And in order to eliminate this bias and calculate an accurate position for the spot, we have 2 weighting rules. Darker pixels and pixels closer to the stellar equator are assigned with higher weights in our computation. Now I will demonstrate how Spot Identifier works. First of all, we will calculate the average gray level for each image, and then we set 2 key parameters. A brightness ratio equals to 90% of the average gray level, and a minimum spot area filter of 50 pixels to exclude noise artifacts. Because the spot needs to be a certain darkness and size in order to be considered real instead of noise artifact. And finally, the program will detect the dark spot features and draw contour boundaries next to the spot. And it will also mark the coordinate of the centroid sequentially. Here is an awesome video of how cool and fast this program works. And also for a stellar map, Spot Identifier outputs the total number of detected stars and marks all the star spots, and mark all the spots sequentially from left to right. The program extracts the XY centroid coordinate and converts them into stellar latitude and longitude. It also calculates the individual area of the spot and sums up to the total spotted area, and finally calculates the filling factor. And the filling factor is the total spotted area divided by the total stellar surface. Once Spot Identifier finished analyzing the star rotation images, it saves all quantitative results into an organized text file for future research analysis. As you can see in the picture, we contain the picture name, which help us to find the picture easily in the future, the value of filling factor, longitude, latitude for each spot. And of course, you guys might have a question. How do we know whether the data we got from the program is reliable? Well, we generate synthetic artificial star images where every spot's location and size is perfectly known in advance. And then they feed those test images to the program. And then we compare its output coordinate with the true data to quantify the detection precision and measurement errors for our algorithm. And this verifies that it works. For our future steps, we will apply our code to artificial starlight curves to test their capability before applying them to Kepler data. Analyze our results to look for trends in spot coverage, evolution, and how they relate to the standard parameters. Using spot latitude and longitude data to study differential rotation, which means rotation period is different for different latitudes. And this is thought to play an important role in magnetic field generation in stars.
So a special thanks for NASA for the funding support, a special thanks to Perkins Observatory for the equipment support, and a special thanks to our wonderful advisors, Dr. Harmon and Dr. Giroux.